Hi everybody, this is the first of two videos that cover the idea of relative standing within a distribution. There are two ways we measure that. The first is percentile rankings, and the second are what are called z-scores, which we'll get into in the next video. So with that said, let's talk about what a percentile ranking is. This is probably something that you've heard of before, but unfortunately there's actually two accepted definitions for percentile, and they're very close to one another. So you really need to focus on what it says in your particular book. In my class, we use that first definition. So the percentage of values that are less than a given value, so specifically to the left of your given value. The second definition is the percentage of values that are less than or equal to a given value. Thank you, math, for not making that confusing at all. So that is everything at your position or even further to the left of that. Usually on the AP test, this is going to come up in the context of we've got a continuous distribution, one where you can draw it without lifting your pencil. And in those particular cases, it actually turns out that it doesn't matter if it's less than or equal to. It works exactly the same. But for discrete distributions, this actually matters quite a bit. So let's jump into an example and show you what I mean. Okay, so we've got a table here that shows the quiz scores of everybody in a class of 20 people. You can see we've got a bunch of 15s and 12s and blah, 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 blah. And we're asked, if you scored a 14 on the quiz, what is your percentile rank? So again, what we need to know is how many scores are to the left of 14 if we were to graph this and say a histogram or a dot plot or something like that. The best, most efficient way to figure this out is to plug those values into your calculator and use the sort A command to figure out just how many values are less than that. I've done that. If you don't know how to do that, I'll have a video up about how to use the sort A and some other useful features on the calculator. So what I figured out is that there are 7 values that are less than, or actually in this case less than or equal to, because there's only 114 in the distribution. So 7 values are less than or equal to, or simply less than 14. There's 20 values altogether, right? Class of 20. So our percentile rank is the 35th. So this is the 35th percentile. Now, this is where it's going to get tricky. If we move on to the next one, if you scored a 15, what is your percentile rank? Well, now less than or equal to is very different than less than. If we go with less than, there's now 8 values out of 20, so this is less than. So that puts us in the 40th percentile. But if we use the less than or equal to, that adds a whole bunch of other values, right? You can see all these 15s in there, and it turns out, I'm not going to go through the math, but that is going to be the 60th percentile. So again, it really doesn't matter which book you're using and which definition they want you to use. So in the next few slides, I'm going to show you some things that are important to know about percentiles. And the first of those is percentiles don't know the context that you're dealing with. They're stupid. They don't know if a high percentile is good or bad, so that is your job to decide. So here's an example where we've got a graph that I haven't labeled anything on, except this red line that indicates you are here in this distribution. Now, is that good or bad? I have no idea because I don't know the context of the problem. So for example, here we are with a distribution of test scores. And now being where that red line is pretty good. You beat a lot of the class, like the vast majority. But if I change that x-axis to read time to run a race, now that percentile being high number is bad for you, right? The longer it took you to run the race, the more people finished before you in time, to your left in time. That gives you a high percentile, but a bad result. So it's very important that you understand the context of the problem you're in. Here's another example of the concept I was just talking about. So we've got the table below that shows the number of times 20 preschool students tried before they were finally able to tie their shoes correctly. We see in particular one student who we're interested in needed 9 attempts before they were able to tie their shoes correctly. So we're supposed to figure out the percentile ranking and explain the value in context. So I've already put this data in order in my calculator, and I know that there are 8 values less than it. So that's 8 out of 20 for a percentile ranking of 40. So this is the 40th percentile. All right, so what does that mean? That means that 40% of the group required fewer attempts than our student in order to tie their shoes correctly. Does that make our student better than average or worse than average? Well, in context, the more mistakes you make, the worse you did, right? So he needed 9 attempts, but more than half his class required more attempts than that. So this is a good thing in this context. 40% of the students required less, which means the majority of the students made more mistakes when tying their shoes than our student did. And I kind of answered the second bullet point along the way. What does it say about a preschooler if their percentile is high in this context? Well, if their percentile is high, that means very few students required more attempts before they tied their shoes correctly. And that's kind of a bad thing, right? We want to be able to do things right more quickly. And then a low percentile means the opposite. If you're the 10th percentile in this context, that means very few students required fewer attempts before they were able to tie their shoes correctly. So context is everything. That is a recurring theme in AP Stats. Another thing you need to know about percentiles is how to find or approximate them at least from a graph. So let's just take a look at an example of this. So in this example, we can see the cumulative relative frequency graph, which shows the distributions of ages in an apartment building. And I should have labeled my axes, so let's go ahead and do that real quick. This is the cumulative relative frequencies, and I'm going to be lazy and abbreviate that RF. And down here, we've got the ages of our tenants. Okay, so I want you to notice the cumulative relative frequency is always going to end at 100% because you've got everybody when you get to the 100th percentile per se. Okay, so what is the approximate age? Oh, that's terrible. What is the approximate percentile of a 45-year-old? The approximate percentile of a 45-year-old. The way I'm going to do that is I'm going to go to the age axis and I'm going to locate 45, and I'm just going to draw a little line going up there. And then when I get to the graph, so like right there, I'm going to cut across to the left to the y-axis, excuse me, and I'm going to see that's, I don't know, that looks like approximately the 60th percentile. Okay. And that's it. So now the next question says, what is the approximate age of a person in the 30th percentile? So now I'm going to work backwards. I'm going to start at the 30th percentile, which looks to be right about here. I'm going to cut across to the right until I hit the graph, and then I'm going to draw down, and I'm going to see that that's what, about 38 years old. So approximately 38 years old. Okay, and then lastly, I'm supposed to figure out what's the approximate IQR. Now, I promise you when you do this, there's going to be an answer choice that trips a lot of people up. So what you need to understand about the IQR is it is a single value. It is Q3 minus Q1. Well, Q3 is the 75th percentile, so I'm just exactly doing what we did on the last one. I'm going to start at the 75th percentile. I'm going to cut across the graph until I hit the curve, and I'm going to go down, and that appears to be right about 55 years old. So Q3 equals 55, and then Q1 is the 25th percentile, so exactly the same procedure. And oh wow, it looks to be right about 35, so let's just call that 35. And a lot of people will say the IQR is 35 to 55. But the IQR is 20. The IQR is Q3 minus Q1, and that is 55 minus 35, so the answer is 20. The IQR, folks, is 20. Okay, please don't mix that up. I guarantee that'll be an answer choice on the test that says 35 to 55. All right. One last thing I want you to know about percentile is there are situations in which they do not tell enough of the story, and you're going to need some better tools at your disposal. Here's what I'm talking about. So let's look at this graph. I haven't given you any context here, but I think this is good enough to make the point. let's figure out about where the 20th percentile is. So 20% might be somewhere around here. So what I'm saying there is the area to the left there is about 20% of the whole curve. That's probably a terrible estimate, but that's okay. And the 10th percentile would be somewhere, I don't know, around maybe here. Okay? Now think about where we are on the x-axis, right? We're talking about this little sliver of the graph, which ain't very much. Now, if I talk about the 80th to the 90th percentile, and I guess I should be more clear here. I'm talking about the difference between those x values here, right? Now, if I go to the 80th percentile, well, this is very right skewed. So maybe the 80th percentile is there. So I'm saying that I think about 20% of the data lies in that space there. That might not be accurate, but again, I'm just doing this to show a concept. And maybe the 90th percentile is there. So I'm claiming maybe 10% is in that space there. Well, look at the difference in the x values in this space on the graph versus this space on the graph. That's a big difference in x values, but the area contained in those two is approximately the same. At least that's my claim. That's my, eyeball claim there. So this is telling me that I need a tool that is a little bit more precise in this, and that's why we need the next video on the z-scores. So I will see you in the next one, and I hope this was helpful.